Have a look at reversible reactions and equilibrium. So some chemical reactions are reversible, meaning that they proceed in both the forwards and the backwards direction. So if you take an example, if you add the two chemicals A and B, they might be able to react to form two other chemicals, C and D, but also C and D can also react together to go back and form A and B. So it's completely reversible, that reaction. And these reactions can either be endothermic or exothermic. And if the forward reaction is exothermic, that means it transfers energy from the reactants to the environment, normally in the form of heat. Then the backwards reaction will be endothermic. So it's always going to be the opposite. So if forwards is exothermic, backwards is endothermic. And guess what? If the forwards is endothermic, then the backwards is exothermic. And in terms of the conservation of energy, so energy will always be conserved during the chemical reactions. And by that, I mean that any energy that is released or absorbed, that will always be equal to what is released or absorbed in the opposite reaction, so the backwards reaction. So say if a certain amount of energy is given out in the forward reaction, then that same amount of energy will be taken in the backwards reaction. So a reversible reaction is a reaction that can proceed in both forwards and backwards direction. An endothermic reaction is a reaction that transfers energy from the environment to the reactants, and normally that makes some sort of cooling effect in the atmosphere. And a something reaction is a reaction that transfers energy from reactants to the environment, normally in the form of heat. That's an exothermic reaction. Now, remember that reversible reactions can proceed in the forwards and the backwards direction. And another way of saying that is something called equilibrium. Now, dynamic equilibrium is when a reversible reaction happens, but within a closed system. And the dynamic equilibrium is what the sort of middle ground that will be reached between the reactants and the products. And that can change. So what will happen is at that point, the amount of product being created, the forward reaction being created, will be exactly the same as the amount of backward reaction being created. So what will end up happening is there'll be no net change of the products and the reactants. So at equilibrium, both forward and backward reactions still happen, but the concentrations of reactions and products remain consistent. Therefore, we describe the equilibrium as dynamic. In a closed system, if a reversible reaction takes place in a closed system, dynamic equilibrium will be reached. Reversible reactions, remember, they can happen in both the forward and the backwards direction. Now, which type of reaction transfers energy from the reactants to the environment? Now, remember, that's giving out energy, and normally in the form of heat when it comes to reactions, so it'll be exothermic. At equilibrium, both forward and backward reactions still happen, but the concentrations of reactants and products remain consistent. Therefore, we describe the equilibrium as dynamic. Now, changing the conditions of a reversible reaction affects the position of the equilibrium. Now, that means, don't forget, the position of the equilibrium is how many products and how many reactants you've got in this closed system. The relative amounts of substances in a reaction at equilibrium are determined by the conditions. Now, this famous scientist called Le Chatelier, he came up with Le Chatelier's principle. And what that says is that any conditions of a reversible reaction at equilibrium are changed, the system will change to oppose the change. The principle is used to predict the outcome of any changes imposed on a system at equilibrium. Now, it's quite difficult to understand that. So the system will change to oppose the change in the conditions. So what that means is if the forward reaction is an exothermic one, so giving out energy, if you put more energy in to that system, then that will push the reactants, push the equilibrium in the endothermic direction to take in that energy. What determines the relative amounts of substances involved in a reaction at equilibrium? Well, it's not whether the reaction is reversible. It could be whether the forward reaction is endothermic or exothermic. It could be the number of moles of gas, potentially, and it could be the conditions of the reaction. Now, I think overall, the most accurate answer will be the conditions of the reaction, because that was what will affect it. Le Chatelier's principle says that if any conditions of reversible reaction are changed, the system will shift to counteract this change, and that will remove the equilibrium temporarily until it's reached again. And then we can return to equilibrium once the system has had time to adapt to that equilibrium. So to remember, dynamic equilibrium is when the rate of the forward reaction equals the rate of the backward reaction, and a closed system is a system in which reactants and products can neither be added or removed from that system. Changing the conditions in which a reversible reaction is taking place can affect the position of the equilibrium. And what do we call a system in which the reactants and products can neither be added or removed? Now remember, that's a closed system, so nothing can be added, nothing can be taken away. And that's when you get dynamic equilibrium. Changing the conditions in a reversible reaction can affect the position of the equilibrium. Remember, that's just how much of the reactants and the products we've got in the system. What is the name of the principle that describes what will happen when a condition or condition of a reaction at equilibrium is changed? Now remember, that was Le Chatelier's principle. I'm just going to make sure I get the right spelling here. I believe it's this one. Le Chatelier was that famous scientist, remember? Now remember, at dynamic equilibrium, the rate of the forward reaction equals the rate of the backward reaction. And why is chemical equilibrium described as dynamic? Now remember, that's because it's not just stopped still when it reaches dynamic equilibrium. It's still moving forwards and backwards, the reactants and the products, but those will be happening at the same rate. So both forward and backward reactions still happen. And that's the end of the session. Join us again next time.